Hello viewers and my dear students. Welcome to session 1 on problems on analysis of beams. Now I'll be showing you a demo on simple beam supported at the ends subjected to transverse loading at the center using Ansys Release 14 of Mechanical APDL. These are all offline video help files prepared by me, Dr. B. Gurudat, former professor and head, Department of Mechanical Engineering, Bangalore Institute of Technology, Care Road, Bangalore 4, presently working as professor at the Department of Mechanical Engineering, Nitte Meenakshi Institute of Technology, Elanka, Bangalore 64. Now, before we start with actual doing of the problem and answers, okay, first we'll know in a simple way what exactly is a beam. Okay, now you see here, a beam is a long, slender structural member generally subjected to transverse loading. That means perpendicular to the axis there will be loading. Okay, so members subjected to transverse loading and produces significant bending deformation. These things anyway we'll do it in the problem and all that. Long horizontal members used in buildings, bridges and shafts supported in bearings are some of the examples of beams. Okay, please understand beam is a long slender structural member generally subjected to transverse loading. That means transverse loading is the load which is perpendicular to the axis. Anyway, this on this we'll take up a problem now. Now you see here the problem is this. The problem one, a beam is subjected to transverse loading as this. This is a beam. Beam is AB and the span length is 4 meter. It is supported at the ends, okay, at A and B. At C, at the middle point, you have a transverse loading of 20 kilonewtons. Okay, now you see here, a beam is subject to transverse loading as shown. Determine the following, assuming beam has a rectangular cross section, 0.2 into 0.3, that is 0.2 width and 0.3 depth. Okay, assume E to be 210 GPa, that means assume this to be steel. Poisson's ratio is 0.27. Use Ansys Mechanical APDL to find the following: deflection curve of the beam, reaction at the supports, bending moment and shear force diagrams, bending stress diagrams, and also find maximum bending stress using theoretical procedures. Okay, these are all the common questions asked anywhere, whether it is VTU or any autonomous examinations and all that. This is a simple problem which you have to do, and you have to do it carefully, because in case, because we are using beam 188 element, if you go wrong in the procedure, you will never get the answer. That's why carefully follow the procedure. Now, before we start doing all this, okay, I show you in a simple way. For this, how exactly bending moment diagram is drawn, shear force is diagram is drawn, and what exactly is the maximum bending stress, what exactly you can get for this and all that. Okay, now this is the thing you just see here. Now this is the problem. AB, the length is 4. Okay, let us say RA is the support here, that is reaction here. RB is the reaction at B, and at the middle you have 20 kilonewton transverse load, correct? Is it okay? 20 kilonewtons transverse load. Okay, now you see here, now you will solve for RA and RB. RA plus RB is 20 kilonewtons. Okay, you see here RA plus RB is 20 kilonewtons. Then you take moment about B, RA, whatever is that. Okay, RB into 4, taking moments about A, RB into 4 minus 20 into 2, if you, that is equal to 0. Okay, RB into 4 minus 20 into 2 equal to 0. And in that way, RB you find out 10 kilonewtons or 10,000 newtons. So since it is RA plus RB is 20 kilonewtons or 20,000 newtons, okay, then once RB is 10,000 newtons, RA will also be 10,000 newtons. That is why RA will be 10,000, RB will also be 10,000 newtons. They are the reactions. This anyway we will find out using Ansys also. Okay. Now you see here, shear force diagram calculations. When it is up, when you take any section here, if there is any force up, we'll take it as positive. That means if you take any section here, to the right of it is RB, that is 10,000 newtons. That means 10,000 newtons you draw here. That is, this is the shear force diagram. Then at this point, this is, at this point you see, anywhere between A and C, if you see it as, this is my 10,000 minus 20,000, okay, That means minus 10,000 you get. That means in this particular portion, it is minus 10,000. In this particular portion, it is 10,000. I'll repeat. And if you take a section between B and C, upward force we take positive. Okay. Then in that way, between B and C, the shear force will be 10 kilonewtons or 10,000 newtons. That is this. Then anywhere between A and C, if you take, okay, to the right side you calculate. RB, this is plus 10,000. But here you have minus 20,000, 20 kilonewtons, minus 20,000. This is 10,000, minus 20,000, it is minus 10,000. In that way, shear force diagram you should get like this. Okay. In the same way, you please understand, RA, RB, they are the supports. At that particular portion, bending moment is 0. Then bending moment at C will be maximum because it is at the middle. Naturally, it will be maximum at the center. Then bending moment at C is RB into C. Okay, bending moment at C is 20 kilonewton meter into, that is RB, that is the bending moment at C is RB into 2. RB is actually 10,000. 10,000 into 2, that is 20,000 Newton meter. That means at this point, okay, at C, the bending moment diagram will be like this. Here 0, here 0. You draw by a straight line here, draw by a straight line. There is like a sort of a triangle here. 0 to 20,000 linear way, 20,000 to 0 linear way, because at the support you have the bending moment will be 0. Bending moment, it is the force into distance. Okay. In that way, bending moment at B is 0, bending moment at A is 0, bending moment at C is RB into 2. RB is 10,000 into 2 is 20,000 Newton meter. That is, this also we'll prove it later on. This is shear force diagram. This is bending moment diagram. This anyway, we'll prove it later on using Ansys. Okay. Now you see bending stress diagram. Bending stress diagram also we'll do, and we'll find out what is the maximum bending stress. As maximum bending stress is M into Y by I. M is bending moment. Bending moment, maximum bending moment. Because maximum bending stress you are taking, no? Maximum bending moment is, as you see here in the previous slide you have seen, it is 20,000 or 20 kilonewton. Okay. 20 kilonewton meter or 20,000 Newton meter. Whatever you put. Okay. Here 20 kilonewton. Y is 0.3 by 2 because the depth of the beam is 0.3. Width is 0.2. 0.3 by 2. BD cube by 12. 0.2 into 0.3 cube by 12. You get like this. 6666.6 kilonewton, because this I have taken kilonewtons. I'll multiply by 10 to the power of 3. It is 6666, that is 6666.6 into 10 to the power of 3 Newton per meter square. Okay. Or if you carefully observe, it is 6.6 into 10 to the power of 6 Newton per meter square, or 6.6 MPa. This is the answer what you should get in Ansys also. Please remember that is maximum bending stress for this problem will be 6.6 MPa. What I have shown you here. These are all the things what you have to prove using Ansys also. Okay. Now we'll go for answers. See here, as usual, I have created a fresh file name. Okay. In the name of Gurudat Bain. And if you see the, and also see here, beam analysis problem 1. I have given, okay, beam analysis, the title, I have even changed the title, change job name Gurudat Beam I have given, and change title, I have given beam analysis problem 1. Okay. And if you see the list of log file also, you see it, up to beam analysis problem 1 has come. Okay. Only up to that I have done. Okay. And as I have told you, whatever you get, whatever you do by graphic user interface, all will be recorded here. You can copy this and paste it here and do the analysis again. You can change the model, you can change the loading conditions, still do. That means analysis will become easy if you operate this log file. Okay. This I have told you already in the one-dimensional problems. You please go through that, because that is not there for your exams and all that, but you are supposed to know all that. Okay. Now anyway, see here. Now I'll go for preferences, structural, okay. Okay. Preferences, structural, okay you do. These are all, this is step-by-step procedure of Ansys. Okay. Preprocessor, element type, add, edit, delete, add you go. Now it is beam, no. Beam, what will support our analysis is this. Beam 2 node 188. Remember, this is the element which will support our analysis. Compulsorily take beam 2 node 188. You say okay. Okay, then you just say close. Okay, beam 188 element does not ask for real constants. That is why that real constant will provide separately. Then we go for material properties, material models, okay, structural, linear, elastic, isotropic. You see what exactly is the problem given. It is 210 GPa and 0.27, correct, no? That is E 210 GPa, that is 210 into 10 to the power of 9 Newton per meter square, or 2.1 E11 you should put, okay? In that way, material models, (2.1) E11 I'll put, okay? And Poisson's ratio is 0.27 you put, whatever is 0.3, 0.3, 0.3, 0.27, 0.27. In that way, you put this. Material is only one, it is only steel, 2.1 e to the power of 11. It is Newton per meter square, you understand. That is why now the loading should be in newtons and the model should be in meter. That you carefully understand. 2.1 e to the power of 11. Poisson's ratio is 0.27. You just say okay. Then you say material exact. Okay. This you do. Now go for sections. This is a very important thing because beam 188 directly asks for the cross section. Beam, sections, beam, common section you take. Then whatever section you want, you have here. You see here, so many sections you have. Anything you take. Now I have square section or rectangular section. In that way, what is breadth you see? 0.2. The breadth is 0.2 and depth is 0.3. Okay, see here, what they are given in the problem is breadth into height. Breadth is 0.2, height is 0.3. This is breadth into height, 0.2 into 0.3 is the problem given. You apply this. You just say okay. Okay, now once you do this, okay, then you go for modeling. Modeling, create key points in active coordinate system you do. Okay, in active coordinate system you do. See here, 1, 0, 0, 0 you take. Just say apply. Then say take 2. 2, it is 2, 0, 0 you put. Then 3, 4, 0, 0 you put. Then 4, you take 4 minus 1, you take this. That means you'll have 4 section points, that is 4 key points. Okay, 4 key points you have. Why this key point has been provided, I'll tell you later on. Okay, now I have created 4 key points and this key point I'll use it at one particular stage. That particular stage you understand later on. Now what I'll do, create lines, straight line. I'll create line to line, from here to here. From here to here also I'll create. Okay, then say okay. I created lines. Okay, after that, you see here, now I have created lines. Okay, I have created lines. If you say list key points and all that, okay, coordinates only. You see here 0, 0, 2, 0, 4, 0, 4 minus 1. Everything is okay. Okay, and if you see list material properties also, properties, all materials, 0.21 or 2.1 e to the power of 12. It is correct. Okay, or 2.1 E11. Okay, 0.21 e to the power of 12 or 2.1 e to the power of 11, 0.27, everything is correct. Okay, now this is, we'll continue in session 2. Now we have come to the end of session 1 and we'll continue this problem in session 2. Thank you very much for watching. Thank you friends. Thank you.